Hello everyone, good afternoon. Today I'm going to talk about my project. It's about the impact of high modulation on the delivery accuracy for IMRT and VMAT radiotherapy plans. It's about simply calculating modulation complexity score. I would like to thank my supervisors Pejman and Sivakumar. So I'd like to break down my thesis title. So it's about so for IMRT and VMAT, as we know all about the treatment therapy modality, which are quite common nowadays. IMRT is called intensity modulated radiotherapy, and VMAT called volumetric modulated arc therapy. So IMRT has the intensity is modulated along each segments in an arc, and the segments are selected during the treatment planning. VMAT is similar to IMRT, but it changes along the whole arc with the control points. The intensity being modulated along the whole arc. So the major differences between IMRT and VMAT are like for IMRT it's the beams the beam is differentiated into segments, and for VMAT it's control points. IMRT has more monitor units while VMAT consumes less. Fixed gantry angle for IMRT and VMAT it's dynamic because it's moving along. So the impact of high modulation is simply about the modulation of the plan, which is based on the increase in monitor units and MLC leaf variability of the tumor size and shape, and also the segment size. It also depends on gantry speed and also dose rate and also collimator angle for VMAT plans. The modulation depends on the complexity. It has been studied in various studies. If the increase in modulation directly relates to the increase in complexity, so and simply increase in complexity decreases the dose to tumor accuracy. This can be measured by gamma index analysis, which is simply variation in prescribed and delivered dose, which is measured by comparing the planned dose from the TPS and also the delivered dose, which is measured by some phantoms 2D array or something like that. So this is one of the gamma index analysis to measure the delivery accuracy. So this one here, it's measured by EPID, and the reference is from TPS, which is the bottom one. And as you can see, there is a variation in the profile from the reference and the target. That variation is taken into account by the gamma index analysis, which give it to a value of in percentage and also in millimeters. The millimeters is about how far it is from the actual dose from the pixel, and the percentage is how many pixels are off from that range. This is used to give out gamma pass rate, which in our hospital SCGH it uses 3% and 2 millimeters, and if it passes if the confidence interval, if the overall confidence interval is above 95%, it can be proceeded to the plan. If it is 90 to 95, it is sent to the action to optimize the plan. So the significance of this project is about if it is implemented, this complexity score is implemented with the treatment plan QA, pre-treatment QA. It will primarily reduces the workload and time of physics because it reduces the dosimetric verification of all the plans, and it can reduce pre-treatment QA requirements, which can like as I said, when it is implemented, it is measured before the dosimetric verification, which is the gamma index analysis. So after finding correlation and implementing this modulation complexity score, we can avoid less complex plans for pre-treatment QA. That is a possibility. It's not a compulsory, but it's a possibility. That will reduce the QA requirements, and also it increases the LINAC lifespan, because every time the LINAC is operating, it is using its life. It improves the overall treatment quality, and also dosimetric accuracy will be improved, because if we focus on high complex plans such as head and neck or something like that, that will optimize the treatments, and also it will increase the dosimetric accuracy of those plans, while wasting time on less complex plans. Provides overall efficiency in the treatment planning, which is pretty much the quality. And also the code which I'll be creating can be altered for new treatment modalities, like other treatment modalities, let's say flash or something, if possible, with the parameters. And also if I can prove the correlation between the modulation complexity score and the gamma index analysis, that will also support other studies which have already proved that there is a correlation. So the primary aim of this project is to create a MATLAB code to calculate MCS for both IMRT and VMAT plans in the Charles Gardiner Hospital. So I'll be using DICOM files, and then I'll be using MATLAB. And also the secondary aim is to find a correlation between MCS and gamma pass rate. And so this is from one of the studies I have referred, and this here it clearly shows the correlation from MCS and gamma pass rate. I think this is for all the organs. It's for all the organs. It's not site specific. So modulation complexity score. MCS it's one of the complexity metric which are currently in use. There are other metrics such as monitor units or modulation index or leaf variability. There are various other metrics which are used. But why I'm choosing modulation complexity score is because it takes into account of the MLC variability and also the monitor units. It weights the MLC variability according to the monitor unit segment weight, segment or control point weight. So that is one of the advantage. And also it has been studied by various other studies and has been implemented in various other hospitals. So it is derived by actually it is derived by McNevin in 2010 for IMRT plans, and it has been studied for various site-specific, organ-specific, and also site-specific treatments. And also it has been developed for VMAT plans in 2013 by Marcy. It incorporates monitor units, leaf segment variability, and aperture area variability, as I said before, with the segment weightage, which segment or control point weightage. So simply it will be a score between 0 and 1, like 0 being the highest complex and 1 being least complex or no complexity at all. So 1, you can if there is a plan with no complexity, you can imagine a field with no MLCs in between the field. And so this gives you a simple ideology of how it looks like. The intensity varies. For least complexity, it's not very high in between. Like for the highest complexity, you can see the intensity being heavier in between. It's changing a lot simply. So the parameters required for the plan will be a DICOM-RT file from the TPS, and from I'll take the parameters such as leaf positions, which can be used to calculate LSV, AAV, and MCS. There are formulas which have been derived by McNevin and Marcy for both IMRT and VMAT. For VMAT, it also includes gantry speed, dose rate, and collimator angles, because in VMAT everything is varying along the way. Yeah. So these are some of the formulas I would like to show. Like, there are lots of formulas. These formulas are for the IMRT plan, which are derived by McNevin. So first we will calculate the position, maximum position, using those. If let's say this is the MLC, the red block on the left bank and the blue block on the left bank will be the left maximum and the right maximum of the left bank, and similarly the vice versa for the right bank. Those values can be used to calculate the maximum position in the left banks, and then LSV uses the same for same values, and also N, capital N means the number of leaves in the collimator, and then similarly used to calculate AAV, and then MCS, which is just the product of the all the three, with the segment being weighted for monitor units for the total for the beam, and then the beam is weighted for the total plan with the monitor units. So this here you can see if how it is if MLC is varying, how you can how it will change the intensity of the intensity map with. So this is actual fluence map for a 4-dimensional VMAT plan, I think. So you can see the intensity being varied, and that graph, it's about it shows the modulation complexity for the top one shows for breast plan, and the bottom one is for lung. So the breast plan is, you can see the MCS lies in the range between 0.8 and 0.9. So you can have a range for site-specific, organ-specific treatments, and that can be used as a threshold for defining pre-treatment QA for other organ-specific sites. So literature I have reviewed, or these are some of the literature I have reviewed, and McNevin and Marcy are prominent one, which derived these MCS for both the plans, and also they have compared with gamma index analysis, which I would like to do for my research too, and they have found a correlation, but not very strong. All these studies have found correlation, but very weak correlation. And also Marcy has proposed some potential candidates for collimator angles, control points, and also collimator angles for the improvements in dose accuracy. Sumida also compared MCS for different organ-specific sites, and also compared the dose delivery accuracy for those organ-specific sites. Rajsekharan has compared for the correlation has found the correlation between gamma index analysis and the modulation complexity score, and and also all those studies have suggested that this can be used as a threshold for avoiding pre-treatment QA for not a pre-treatment QA, but dosimetric verification for less complex treatments. And Park has compared other modulation indices, such as I said before, modulation index and leaf travel modulation complexity score, which is just the modulation complexity score along with the leaf travel. And he has also found some correlation between gamma pass rate and indices. So the code map as I have right now in mind is about treatment planning system, how to take the parameters from the TPS and anonymizing the patient information, and then from those data I have to recover LSV, AAV, and those using the formulas I have talked about before, and that I should implement it into the MATLAB as a code, and then that will create a modulation complexity score. On the other hand, I have to, for the second step, I have to create the gamma index percentage that will provide gamma pass rate, and at last I would like to make a graph which is against gamma pass rate versus MCS, which other studies have done. Here, this is a study plan. Yeah, verify data and then creating code. So hopefully I'll be completing these codes around this summer, or probably half of the next semester, halfway through the next semester. And then just inputting those parameters and finding them complexity score, and then comparing the gamma pass rate. I think that wouldn't take long, probably around the end of the next semester. And then using statistical analysis, I had to find correlation, and then that will be my result. Hopefully, I'll submit my thesis around next year end, and then, if possible, publish an article. Thank you for your presence.
Questions? All of these plans will be done on Monaco?
Monaco?
Monaco TPS, or which TPS you are going?
Okay, I haven't considered that yet, because yeah, it is TPS. The TPS should be
here in the SCGH.
Yeah, yeah.
Because we have a new TPS also, it will be good to work on this.
Okay, because there are studies which have compared between different TPS. I think I'll be using one. I don't know. I'm not sure.
So another option is joiner files.
Joiner files also on the machine.
Okay, any other questions?
Thinking of any, go ahead. Sorry. No, go ahead. So your correlation between the gamma pass rate and the MCS.
Yeah.
How do you expect your setup error in the patient-specific QA to impact that correlation?
That's a tricky question.
Do you account for that?
Like, no, as of all the studies, they haven't accounted for those variations. I think those variations have to be, like, if you're not comparing with so this comparison should be done for retrospective like plans, not the current ones, and then it will provide a solid evidence that there is a relation. Then it can be implemented. But also it is site specific. Every LINACs are different and every sites are different. So, yeah.
So the studies looked at, they looked at the site-specific effects.
Yeah.
Did they look at things like the size of the target? Does that?
Yeah, they did. The size of the target for the specific organs, like let's say head and neck, they considered around at least 40 or 50 plants.
Yeah.
And then they found the correlation. Like when they graphed it, it is pretty much lying in the range of a complexity score. So yeah, they have found for different sizes and different shapes of tumors.
Potentially you could look at that too.
Yeah, I think so.
To extract the RT structure files from
Yeah,
the plans as well.
sure.
Is the idea to develop the code for any particular one site, or is it your program or your coding will be fitting for all sites, or it's too early?
I think it will be just for this site, because other studies, they have also created the code, but they have specified that it's site specific, because every site uses different parameters and what do you call, like constant values, right, for each site specific. So I think this one is site specific, but it can be improved for globally. I'm not sure.
If it's site specific, do you have any idea which sites you're going to be focusing on?
Okay, site specific in the sense this site, Charles Gardiner, or Argonne.
Treatment site, yeah.
Anatomy.
Huh?
Anatomical site.
Anatomical site. Okay. I think I can look out for different anatomical sites, because it's using the same formulas. It doesn't differ. So I think I can look out for anatomical site. Sorry, I thought different.
No, we talked about anatomical site.
Okay.
Okay, any other questions?
Thank you.